Welcome to our deep dive. We're tackling neutron stars today.
Yeah, neutron stars.
You look at some really interesting stuff in the sources.
Definitely some cool stuff in there.
So, where do we even start with these things? They're like, what, the leftover cores of dead stars?
Right, but imagine this. Take a star way bigger than our sun, like at least 8 times bigger.
Okay, got a giant star in my head.
Now crush that star down until it's like the size of a city.
That's insane.
That's a neutron star, a tiny, ultra-dense ball of matter.
So it's like all that stuff from the star crammed into this tiny space.
Exactly, and the density is just mind-blowing.
Okay.
We're talking a teaspoon of neutron star material weighing billions of tons. Billions.
Whoa, okay, back up a second. How does a star even get to that point? Our sources mentioned supernovas, right?
All right, it starts with a supernova. A massive star dies, explodes, and leaves this incredibly dense core behind.
So it's not just any star. It has to be huge to begin with.
Yeah, most stars, like our sun, they'll just fizzle out eventually. But these giant stars, they go out with a bang. A supernova.
So during the supernova, the core of the star gets crushed down.
Yeah, the pressure and gravity becomes so intense that the core collapses in on itself.
And depending on how massive that core is, that's when it either becomes a neutron star
Or
or
a black hole, right?
black holes are crazy.
They really are.
So neutron stars, they're like the in-between stage. Not too big to become a black hole, but not too small to just be a boring old white dwarf.
That's a good way to put it. They're right on that edge, and that makes them incredibly fascinating to study.
But how do we even know what happens during the collapse? I mean, we can't exactly get a close-up view of a star's core imploding.
Well, we have observations of different types of supernovae, each with its own signature.
Okay, so by analyzing the aftermath of these explosions,
We can actually piece together what happened during the collapse.
that's pretty impressive. It's like cosmic detective work.
In a way, it is. But going back to the density of neutron stars, it's all down to something called neutron degeneracy pressure. Heard of it?
Not really.
Basically, imagine trying to squeeze something as much as you physically can. At a certain point, it's going to resist, right?
Yeah, like trying to compress a rock.
Exactly. In a neutron star, the particles themselves, the neutrons, they're packed together so tightly that they resist further compression.
And that's what keeps the neutron star from collapsing further, even with all that gravity trying to crush it down.
Exactly. That's neutron degeneracy pressure at work. It's a quantum mechanical effect, kind of mind-boggling, but it's what makes these extreme objects stable.
Okay, so this pressure is basically nature's way of saying, no more collapsing. You're as dense as you're going to get.
Pretty much. Without it, all neutron stars would just keep collapsing into black holes.
So we should be thankful for neutron degeneracy pressure. It's keeping the universe a little less holy.
I guess you could say that.
But seriously, if neutron stars are this dense, what does that mean for their gravity?
Oh, their gravity is off the charts. It's billions of times stronger than Earth's gravity. Just imagine, it's strong enough to even bend light.
Whoa, light taking a detour. That's something else. What would happen if we got too close to a neutron star? Asking for a friend, of course.
Let's just say it wouldn't be pretty. The tidal forces alone would be enough to rip anything apart.
Good to know. I think I'll admire these from a safe distance. But how do we even see neutron stars? They're not exactly shining like normal stars, right?
Some of them do, in a way. That's where we get pulsars. Those are fascinating.
Pulsars, right. They're like those blinking stars, aren't they?
Yeah, kind of like cosmic lighthouses. You see, as a neutron star spins, it can emit beams of radiation from its poles.
And if those beams happen to sweep past Earth...
Exactly. We see them as pulses of light, hence the name pulsar.
So not every neutron star is a pulsar, just the ones that happen to be pointed the right way.
That's the idea. And it gets even cooler. These beams, they're not just regular light. They can be radio waves, X-rays, even gamma rays.
Seriously? All from something the size of a city?
All powered by the neutron star's super strong magnetic field, which can be trillions of times stronger than Earth's.
Trillions. Our sources mentioned something about a magnetar, whatever that is, being able to wipe a credit card from across a football field.
That's a magnetar for you, a neutron star with a magnetic field on steroids.
Okay, that's got to be some serious magnetic power. So how does that even work with the pulsars?
Well, imagine this incredibly strong magnetic field, right? It acts like a particle accelerator, channeling charged particles out from the poles at nearly the speed of light.
And those particles create the beams we see.
Bingo. The energy involved is just phenomenal. We have this example, the Crab pulsar.
Oh yeah, our sources mentioned that one.
It's inside the Crab Nebula, the leftovers of a supernova that people actually saw here on Earth almost 1,000 years ago.
Wow, 1,000 years ago, that's wild. So we can still see this pulsar today, flashing away.
Oh yeah, it's still going strong, a testament to how much energy these things pack.
Speaking of energy, we touched on magnetars earlier. Those are the ones with the crazy strong magnetic fields, right?
You got it. And those magnetic fields can cause some serious havoc. We're talking starquakes.
Starquakes. Like earthquakes, but on a star.
Exactly. Imagine the surface of a neutron star already under unimaginable pressure.
Right, because it's so dense.
And then that pressure gets even more intense because of the magnetic field causing the crust to crack and shift.
And that releases even more energy.
Tons of it. We're talking massive bursts of gamma rays
Yeah.
detectable across the galaxy.
That's insane. Our sources mentioned one magnetar, SGR 180620, I think it was called, that unleashed more energy in a fraction of a second than our sun does in like 100,000 years.
Yeah, these things are no joke. And they're helping us unlock some of the biggest mysteries about the universe, like what happens when gravity gets so strong that it literally warps space and time.
You mean like with gravitational waves? I've heard about those, but they're usually talked about with black holes, right?
Black holes, neutron stars, any really massive object can create them. But one of the most promising ways to study these waves is by looking at what happens when two neutron stars collide.
Okay, two ultra-dense objects smashing together? That's gotta be.
Explosive doesn't even begin to describe it. We call these events kilinovae.
Kilinovae. I kind of like the sound of that. But how do they compare to something like a supernova?
Way more powerful. Think millions of suns exploding all at once.
Whoa, that's a whole other level of energy. And these kilinovae, they produce those gravitational waves we were talking about.
Yeah, but it's not just energy, right? I mean, our sources said something about kilinovae creating heavy elements.
Absolutely. It's like a giant cosmic forge. When those neutron stars collide, the heat and pressure are just unimaginable.
Like more than a supernova.
Way more. We're talking billions of degrees, enough to fuse atomic nuclei and create elements that wouldn't exist otherwise.
Okay, so what kind of elements? Are we talking like iron, carbon, the usual suspects?
Heavier stuff, actually. Gold, platinum, uranium, the real heavy hitters.
So that gold ring you're wearing, that could have been forged in a kilonova billions of years ago. It's totally possible. It's mind-blowing when you think about it. We're literally made of stardust, remnants of these ancient cosmic events.
Yeah, it puts things in perspective, that's for sure. We've talked a lot about what happens outside a neutron star, but what about inside? That seems like the biggest mystery of all.
It's a question that keeps scientists up at night. Imagine the conditions at the core of a neutron star. The pressure is so intense that it's thought to break down matter as we know it.
Break down matter, as in atoms and stuff.
Exactly. Protons, neutrons, they might not even exist in the same way under those conditions. Our sources mention something called nuclear pasta. Have you heard of that?
Nuclear pasta. That sounds, interesting. What is that, some kind of cosmic spaghetti?
Kind of. It's a theoretical type of matter thought to exist in the crust of a neutron star. Imagine atomic nuclei squeezed together so tightly that they form these long, strungy shapes like spaghetti, or flat sheets like lasagna, even little clumps like gnocchi.
So you're telling me there could be a cosmic Italian feast happening inside a neutron star? I don't know if I should be amazed or terrified.
It's pretty wild, right? And that's just the crust. The deeper you go, the weirder it gets. Some scientists believe the core might be made of something called quark matter.
Quark matter. I'm not even going to pretend I know what that is.
Quarks are these tiny particles, even smaller than protons and neutrons. They're the building blocks of matter, but they're usually bound together very tightly.
Okay, so under normal circumstances, we never see them just hanging out on their own.
Right. But inside a neutron star, the pressure might be so extreme that it actually breaks those bonds, creating a sort of quark soup.
So instead of atoms, you have this soup of dot quarks. That's a lot to process.
It really is. And it's one of the many mysteries that make neutron stars so fascinating to study.
It sounds like there's still so many questions we're trying to answer about these things. Like, what's the absolute limit on how massive a neutron star can be before it collapses into a black hole?
Yeah, that's a big one. And how does nuclear pasta transition to quark matter, if it even does? Every observation we make, every bit of data we collect, it just opens up more questions.
It seems like the more we learn about neutron stars, the more we realize we don't know.
That's the beauty of science. There's always something new to discover.
Well, I'd say this deep dive has been an incredible journey. We've learned about these mind-blowing objects, from their explosive births to their potential to create the elements that make up our world.
And let's not forget those mind-bending interiors. Nuclear pasta, quark soup, it's like something out of science fiction.
If anyone ever invents a neutron star-powered spaceship, let me know. I'm ready for the next adventure.
I'm right there with you. Until then, keep looking up at the stars and never stop asking questions.
That's great advice. And to our listeners, thank you for joining us on this deep dive into the fascinating world of neutron stars. We'll see you next time.